Okay, so chapter 1 was just introductory, pretty much letting you know what is physics. The first part studies motion. If you do have to take part 2, part 2 is more on electricity. All right, so what we've learned is the basic fundamental properties. So mass is in kilograms, time is in seconds, um, length or distance is in meters. All right, so we were learning the basics. We were also converting between different SI units. We were learning about the powers of 10 prefixes. And like I said, table 1.4, if you look at it a little bit every day, it's going to help you when it comes to converting between those prefixes. Okay, so chapter 2 is on motion in one dimension. All right, so the first topic of importance is displacement. So this is a frame of reference between the starting point and the ending point of movement. Okay, so you have a place where you start the change in position, and then you have the place at the end where you stop your change in position. All right, that is called displacement. Displacement is represented by delta x. Right, and delta x is simply the final position minus the initial position. Right, and our distance is just a form of length between 2 points. Right, so again, that is measured in meters. Displace. All right, so sometimes you'll see displacement as d. Most times you'll see it as delta x. Right, and delta x is your final position minus your initial position. Now this is in reference to the x-axis. All right, and we'll put the SI units here. All right, so this displacement, which is your change in your final position to your initial position, that's going to be in meters. All right, so lowercase m. All right, so let me just kind of display a little example of the difference between distance and displacement. Okay, so let's say we have a triangle. All right, each corner is a position. So let's say A, B, C, D. And let's say each side is like 2 meters or something. So from A to D is 2 meters, from A to B is 2 meters. So let's just make everything 2 meters. All right, if we go from point A to point C, we cover 2 meters plus another 2 meters. So that will be 4 meters. All right, the total distance traveled is your total number. So that's your distance between points. All right, the difference with displacement. All right, so let's say we start at A and then we go around the whole thing and we end at A. So let's say this is the starting point and it's also the ending point. So what that means is that our final position, which is A, minus our initial position, which was A, is going to be equal to 0 because we're at the same place that we started from. So this isn't the total distance, because if we did the total distance from A to A, distance from A to A, you would add up that total distance that you traveled. So that would be the 2 plus 2 plus 2 plus 2. So 2, 4, 6, 8 meters. That would be 8 meters. So distance is the total distance traveled from start to finish. Displacement is in reference to your starting point. So if you start at the same point, you go around 360 degrees and you end at the same point, your displacement is 0 because you're in the same place you started from. You've gone nowhere. All right, so that's the difference between distance and displacement. Now, distance-wise, you traveled 8 meters, but displacement-wise, you are in the same place you started from, so there is no displacement. Okay, so displacement is your final point minus your initial point, which here is the exact same. And your distance is the total distance traveled between points. Okay. Does everybody understand the difference between distance and displacement?
Yes, ma'am.
All
Yeah.
right.
Yes, ma'am.
Okay, let me go back to the book. Hopefully I didn't close it. Okay. All right, so we'll go more into vectors in the third chapter, but just to do a brief introduction, a vector has both magnitude and direction. So magnitude means the numerical value, and then the direction means, the direction that you traveled in. And a scalar quantity is simply the magnitude. It's just the numerical value, but it has no direction. So again, we'll go more in depth in chapter 3 on vectors. So I'm not gonna make you memorize that right now. Okay, so the next topic was velocity. Velocity and speed can be used interchangeably, but they mean totally different things. So let's go over that right quick. Speed and velocity. All right, so your speed and velocity have the exact same SI units. Put the SI units over here. Okay, so your speed is your distance, total distance traveled over time, and your velocity is your change in position over time. So your velocity is a vector quantity, and your speed is a scalar quantity. All right, so this is your number value. So let me go back. Put the pound sign for number and value. You guys can write out the word number if you want to, but I was kind of running out of space. All right, so your vector is your number, value, plus direction. Okay, so that's going to be your distance or displacement divided by time. Okay, so if I tell you I'm going 55 miles per hour, I'm giving you my speed. That's the value of how fast I'm going, okay? But if I tell you I'm going 70 miles per hour on Highway 40 West, I'm not only giving you how fast I'm going, which is the numerical value, I'm also giving you the direction that I'm in, because I-40 West is a direction. West is a direction. So don't forget your directions, north, south, east, west, which we'll actually be going more into depth on in the vector chapter, which is chapter 3. We'll get into that as well. So your velocity and speed has the exact same SI units of your distance, which is in meters, divided by time, which is in seconds. So your SI unit for speed and velocity is meters over seconds. right? So velocity is how fast you're going. It is the distance that you're traveling over the amount of time it took you to travel that distance. All right. So the length between those 2 points is in meters, and time it took you to travel between those 2 points is in seconds. So your SI unit for velocity or speed is meters per second. So speed and velocity can be interchangeably used. They just mean slightly different things. So if we write this out slightly different way, that'll be your delta x. So your change in your x, which is your displacement, over the change in time. All right. So delta just means final minus initial. All right. So it's going to be your final position minus your initial position. So that's x sub f minus x sub I, final minus initial. So you're doing that across the x-axis as well as across time. So your final time minus your time that you started out, which is your initial time. All right, so you'll see the velocity equation as d over t or delta x over delta t. All right, SI unit is exactly the same. All right, your position or your motion across the x-axis is going to be measured in meters. And then your distance across the time axis is going to be measured in seconds. All right, these are the basic fundamental properties of physics. Length is in meters, time is in seconds. All right, we haven't gotten into using mass yet, which is in kilograms. So those fundamental properties that we went over in chapter 1, you need to know those. All right, they make up most of the fundamental basic equations of physics. Okay, they also talk about acceleration. Right? Acceleration is how much your speed is changing over time. So whether you're slowing down over time or whether you're speeding up over time. Right? So acceleration is denoted by lowercase a, and it's equal to your change in velocity, so delta v, over the change in time, which is delta t. Now we've already established that delta v is our delta x over delta t. So if we were to plug in that fraction over another fraction, so that's our delta x over delta t over t. All right, anytime you divide a fraction by a fraction, you have to flip the fraction that's on the bottom. All right, so let me write this out in a way that looks a little bit less confusing. All right, we're gonna take this delta t right here, or t, to be understood as t divided by 1. All right, that's the same thing as multiplying the fraction of x over t times the fraction on the bottom. But to multiply times the fraction on the bottom, we would have to flip this. So this would be 1 divided by t instead of t divided by 1. So x times 1 across the top is x. And then t times t is going to be t to the second power because there's 2 t's right here. So this is going to be t squared. And if we do the SI units for x, that's in meters. If we do the SI units for time, that's going to be in seconds squared. So that's the SI unit for acceleration, meters per second squared. So this is how your velocity is changing over time. So if you are driving and you start to apply your brake, you're slowing down. So you're deaccelerating, right? So your acceleration will be negative. Right? If you are hitting the gas while you're at a constant speed, then you're going to increase your speed over time. So your acceleration will be positive because you're accelerating. So accelerating is speeding up, Decelerating is slowing your speed. And then constant acceleration is there's no change in speed. You're doing the exact same speed you were before. Right? Does anybody need me to explain over again how we got to these SI units?
Yes, please.
All right. So let me go back. I'm going to erase a little bit of this. All right, so let's just leave it as V over T instead of the change in V over T for right now, to keep you guys from getting a bit too confused. Okay, so your acceleration is equal to your velocity divided by the time. All right, here we found out that our velocity was equal to the change in X over the change in T. So all I did here in the numerator for V is replace V with X over T. So let's rewrite V to equal to X divided by T. And that's in the numerator. All I did was substitute X over T for V. And then in the denominator, we still have T. So I bring that over. All right, we're treating this as a fraction divided by a fraction. All right, so the fraction that's in the denominator is understood to be T over 1. All right, so if you remember, anything over 1 is just whatever is in the numerator, which is T. Okay, so what I'm doing is I'm rewriting this for our fraction on top to still be X over T, but now our fraction on the bottom is going to be T over 1. T over 1 is still T. All right, so instead of dividing a fraction by a fraction, I'm going to multiply. Okay, so in math, when you divide two fractions, what you do is you just flip the fraction on the bottom and you multiply those fractions together. So X over T divided by T divided by 1 is the same thing as X over T multiplied times flipping the second one. So what was on top is now on bottom, and what was on bottom is now on top, so that we can multiply this instead of dividing this. So it's going to be 1 divided by T. All right, X times 1 is simply going to be X. And then T times T. If you guys remember, when you multiply the exact same variable by each other, you get exponents. So T times T is going to be T squared in the denominator. All right, so the variable for X is the change in position, which is in meters. So X is in meters. And then our time is in seconds. So it's going to be seconds to the second power. So seconds squared. All right, so our velocity, our acceleration, is velocity over time. So it's going to be meters per second divided by seconds, which is meters per second squared. All right, so each equation is going to build off a past fundamental property or equation. All right, so once we start plugging everything in, all right, that's how we come out with these SI units at the end. All right, hope that was a little bit better than my first explanation. And if you forgot how to divide fractions by fractions, don't be afraid to kind of go back and maybe look at a YouTube video for dividing fractions by fractions, just to refresh your memory, because it's a lot of math. So what I did here was just pretty much show you how we came to our derived SI units. But this is not the actual, you don't have to write all that out for the equation for acceleration. All right, it's just velocity divided by the time. All right, so I was just showing you how to derive the SI units. But the acceleration equation is your change in velocity over the change in time. So let me put the delta symbol back here. All right, so our dv is going to be our final velocity minus our initial velocity divided by the final time minus the initial time. All right, so that's what they have here. And it's in meters per second squared for your acceleration. And since velocity is the distance divided by time, that's what's in the numerator, but you have time again in the denominator. So that's where they get the seconds squared from. Okay, so free fall is another word for gravity. So let me block off acceleration so I can kind of fit these on the same page. All right, free fall is another word for gravity. Gravity is denoted by lowercase g, and it's equal to 9.8 meters per second squared. Now, if you notice the SI unit for gravity and acceleration, which let me erase it from this side and put it on the other side. Okay, so acceleration was meters per second squared, and gravity is meters per second squared. So acceleration and gravity have the exact same SI units. Gravity is a form of acceleration in the downward direction towards the Earth's surface. So anything we throw in the air eventually comes back down. So whether it's a balloon or a ball, when you throw it up, it's going to come back down due to Earth's gravity. All right. The gravity of Earth is 9.8 meters per second squared. All right. So the gravity on Earth is different than the gravity on the moon or any other planet. So make sure that you know that this form of gravity is specifically for the Earth's surface. All right, so free fall is just another word for gravity, and gravity is the acceleration in the downward direction towards the Earth's surface. So no matter what object is thrown in the air, when it comes back down, it usually has an acceleration of 9.8 meters per second squared. All right, so acceleration is negative gravity in the downward direction. So sometimes you'll see it as negative, but since most scientists already know that it's negative because it's in the downward direction, they usually keep it as positive. All right. Okay, let me see. I think that was the gist of chapter 2.